In this section, we're solving rational equations. I'd like to consider this equation as our example. X over x minus 1 over x equals 3/2. So to solve this equation means to find a value that we can plug in for x to get a true statement. I'd like to point out that most values for x will not lead to a true statement, and I just give you an example of a non-solution. If we plug in 3 for x, we get 3 over 2 minus 1/3, which is in the end 2/3, which is not equal to the right-hand side, which is 3/2. So 3 is not a solution. So we can solve this equation also graphically. I'm going to turn this into a system of equations. Y equals the right-hand side and y equals the left-hand side. Note that to solve the system, we can do a substitution with the y, and we end up exactly with the equation we started with. The solution to this system of equations is an ordered pair of points, the x-coordinate of which is a solution to our original equation. Okay, why am I doing this? Because I want to demonstrate the graphical approach. So if we are solving this system of equations, we can graph the first equation, which is just a line. That's the red line in the picture. We can graph the second equation. I won't explain how I got this, but you can use a graphing program like Desmos or Maple or whatever. Wolfram Alpha will probably graph that for you. We can get an idea of what the graph looks like there. We don't want anything more than an idea because it's just a matter of counting here. You'll talk about graphing actually much more in the next course, and you'll really know how to make sure that we've got the whole picture. But right now, let's just take the graph I have here for granted. And what we're looking for here then in this system is the intersection of the red graph and the black graph. And this only happens at 2 points, so the solutions are these x-coordinates associated with these 2 intersection points. So we expect 2 solutions in this case. In general, we can't only approximate these if we're taking this graphical approach, but it is helpful to know how many solutions we're looking for, just like when we were solving systems of nonlinear equations. This is another system of a nonlinear equation. Okay, but how do we find these algebraically? How do we find these exactly? We've got 2 methods. The first method is the following. These will be reminiscent of the first and second methods of the simplification of complex fractions. For the first method, what we want to do is simplify the left-hand side and the right-hand side. And we'll get 2 fractions, and then we'll multiply both sides by the least common denominator. And then those denominators will cancel, and we'll end up with an expression which has no fraction in it, which we will know how to solve from previous experience. So here we are. So let's do it. We get a common denominator for the left side. So that is, we multiply the left fraction and the left-hand side by x, numerator and denominator, the right one by x minus 1. That gives us a common denominator of x times x minus 1. And we subtract those fractions. We get this. And in the right-hand side, this is already simple. So we have 3 over 2. Now the next step is to multiply both sides by, see that the common denominator is 2x times x minus 1. So what we will do is multiply left and the right-hand sides of the equality by that common denominator. That preserves the equality. And when we do that, we can see that the x times x minus 1 over x times x minus 1 cancel on the left-hand side, and the 2's cancel on the right-hand side. So we get the following equation when we do that. Here I have distributed the 3x on the right-hand side. We notice that that is a quadratic equation, so our strategy is to collect all of the terms on one side. So I have distributed the 2 and collected them on the right-hand side. We get this. A collection of like terms gives us this simple expression on the right-hand side, which can fortunately be factored. And using the zero product property, we find out that x must be 2 or negative 1. We must check to make sure that this makes sense in the original, and we can in fact check to see that we get 2 true statements. And we do not actually have to evaluate the left-hand side entirely. Sometimes that can get kind of nasty, depending on what the potential solutions are. But what we do have to check is to make sure that the denominators in the original are not 0. As long as they're not 0, then all of the steps will be reversible near those potential solutions. So there won't be a problem. So method 2 is more akin to the second method of the complex fractions. So what we do from the get-go is locate all the denominators that are highlighted here in the equation. That's x minus 1, x, and 2. The least common multiple of all of those is the 2x times x minus 1. We can multiply the left-hand side and the right-hand side by this least common multiple. And when we do that, I'm going to distribute over the subtraction in the left-hand side, and we get this expression here. I've highlighted the least common multiple multiplication process. So when we multiply in the first fraction, I'm going to point out that the x minus 1 cancels. The second fraction, the x will cancel, and the third fraction, the 2 will cancel. So what we're left with on the first fraction is 2x squared. The second fraction, 2 times x minus 1. And on the right-hand side, a 3x times x minus 1. Which is an expression without fractions that will look familiar from what we had before. We distribute, and notice that this is a quadratic equation. We will collect the terms on the right-hand side. We get this. Now we proceed as we did in the last example, or the last method. On the previous page, and we find out that x is equal to 2 or negative 1. But the original expression is not defined for x equals 1 or x equals 0, but these are neither 0 nor 1, so we are okay. And 2 and the negative 1 are solutions to this equation.